will be looking at question 45 of GATE 2020 Chemical Engineering paper. The question is, an aqueous suspension at 60 degrees Celsius is fed to the first effect of a double effect forward feed evaporator with a mass flow rate of 1.25 kg per second. The sum of the rates of water evaporated from the first and second effect is 1 kg per second. Temperature of the exit streams from the first and the second effects are 100 degrees Celsius and 60 degrees Celsius respectively. Consider the specific heat of the aqueous suspension and the latent heat of phase change for water to be 4 kJ per kg per Kelvin and 2200 kJ per Kelvin respectively over this temperature range. The steam economy in kg per kg is given by round up to 2 decimal places. So in this question we have been given a double effect forward feed evaporator and we have been asked to find the steam economy. So in general any double effect evaporator is given by this general schematic. So we have this feed which is basically an aqueous solution that needs to be concentrated, and we provide steam as a heating medium which is used to evaporate the solvent or water that is present in this feed, so that it can be so this steam basically evaporates the solvent or water present in the feed to concentrate it. Yes, so in the first effect the concentrated solution will be again fed as an input to the second effect, and similarly the vapors that have been generated in the first effect are used as a heating medium in the second effect. So yes, practically this steam and condensates are removed from the evaporator, but for our purpose, for energy and mass balance, we will be neglecting these two streams. So now from the given question, we have been given that the aqueous suspension is fed at 60 degrees Celsius. So here the temperature of the feed we have been given as 60 degrees Celsius with the mass flow rate of 1.25 kg per second. So let's just write m dot f as 1.25 kg per second, and the sum of water evaporated from first and second effect is 1 kg per second. The temperature of the exit stream from the first and second effects are 100 degrees Celsius and 60 degrees Celsius. So in the first effect we have been given the temperature as 100, the temperature will be 100 degrees Celsius, and in the second effect the temperature will be 60 degrees Celsius. So both the outlet will be at the same temperature of 100 degrees Celsius and 60 degrees Celsius. So here also temperature will be 100 degrees Celsius. Here it will be 60 degrees Celsius. Similarly here it will be 100 degrees Celsius, and the final product will get out at 60 degrees Celsius. And we have been given this specific heat and latent heat for phase change. So let's just consider if the mass flow rate of the steam is m dot s, the vapor generated in the first effect is V1, in the second effect the vapor generated is V2, the liquid obtains are concentrated liquid obtains are L1 and L2. So for such a case we define steam economy as kg of vapor obtained upon the kg of steam that has been used to vaporize, the kg of steam that has been used to generate those vapor. So that we can write it as kg vapor upon kg steam used. So in this case the vapor generated will be V1 plus V2, and the steam we have considered as m dot s. So the steam economy we have to find these three terms. So for that we will be writing mass balance and energy balance across both of these evaporator individually and then equating them to find the desired values. So let's just start with mass balance. So for this first evaporator we can write that the feed is equal to vapor plus L1, so that we can write it as feed, we are writing it as F is equal to L1 plus V1 for this first. Similarly for second effect evaporator Now my L1 will become the input. So L1 will be equal to V2 plus L2. Now we can replace this value of L1 in this mass balance for operator 1, and we can obtain V2 plus L2 plus V1 is equal to plus L2. Now in the question we have been given that the sum of the rates of water evaporated from the first and second effect is 1 kg per second. That is V1 plus V2 is equal to 1, that we have been given. So we will just replace it over here, and we can get F is equal to 1 plus L2. Okay, so we will be using all this equation to find the steam economy later on. So now we have done the mass balance. So now we will write the energy balance for the same system. So for the first first evaporator, we can write energy balance as okay. So Q can be written as, we can write it as enthalpy of the steam. Okay. So the mass flow rate was m dot s. So we can write it as m dot s into lambda s is equal to this. Basically, the steam will be used to change the temperature of the feed. Okay, so basically this will be liquid, and so if this is F, this is L1, V1, V2, and L2. So the temperature of this liquid stream F will be changed. Similarly, this steam will be used to vaporize this liquid. Okay, so that we can write it as enthalpy of liquid plus vapor, mass flow rate of feed to Cp of feed into the temperature change of the feed will be, so the inlet temperature was 100 degrees Celsius. No, the inlet temperature was 60 degrees Celsius, and in the first effect we had this 100 degrees Celsius. So the enthalpy across here was 100 minus 60, plus we have to write the enthalpy of vapor. So the vapor that will be generated is V1. So this V1 we can write. So usually it is written as m dot f minus this. This is the mass of the liquid into lambda V. Okay, and this term is equal to this vapor. So basically we can write this as lambda s. We have been given it as latent heat of phase change of water as 2200 kilojoule per kg. So this is 2200 into mass of steam we don't know. The mass of the feed we have been given as 1.25. It is over here. Similarly, the specific heat of aqueous suspension is 4 into 40 is plus. Now this, the amount of vapor generated is V1. So this is V1 into lambda V is again 2200. Okay, so we can simplify this equation and write it as 2200 into m dot s minus V1 is equal to 1.25 into 4 is 5, 5 into 40 is 200. So we have this after writing the energy balance over first system. Similarly, we can write the energy balance over second evaporator. So in the second evaporator, this V1 V1 will be used to heat my system. Okay, so that we can write it as Q is equal to uh, V1 into lambda 1 is equal to, now the feed rate will be the outlet of this first evaporator, and that will be L1. So, and the temperature over here was 100 degrees Celsius, and over here it is 60 degrees Celsius. So that we can write it as L1 into Cp into, now the temperature difference will be 60 minus 100. So that we can write it as 60 minus 100 plus, we had this was for liquid, and now we have to write it for vapor. So for vapor generated here will be V2 into, we can write it as lambda V. Okay, so now we can just replace the value. V1 into 2200 is equal to L1 into the specific heat of this suspension is given as 4, so that we can write it as L1 into 4 into minus 40 plus V2 into lambda V is 2200. We can write this as V1 V2 to 2200 is equal to, now we know that V1 plus V2 is equal to 1. So that will give V2 is equal to 1 minus V1. So this we will replace in our equation. It will become V1 minus of 1 minus V1. So this will become 2V1 minus 1 to 2200 is equal to minus of 160 into L1. Now L1 we don't know as of now, but we have the value of feed. So from that, F is equal to L1 plus V1. So from that we can write L1 as, so let's just write it over here. F is equal to L1 plus V1. So L1 will be equal to F minus of V1. So that we can write it here as F minus V1, and we have the value of F as 1.25 minus of V1. So we can write this as 4400 V1 minus of 2200 is equal to minus of 200 plus 160 V1. So from here we can solve for V1. So V1 will become 2000 upon 240. So V1 will become 0.4716. Okay, so we have the value of V1 as 0.4716. Now we can put that value of V1 over here. To find the value of m dot s. So m dot s will be 200 upon 2200 plus 0.4716. So this will, so the mass flow rate of steam will come somewhere around as 0.5625. So now we have this value of m dot s, and we also have this v1 plus vt equal to 1. and then we can find the steam. We can write the steam economy as V1 plus V2 upon m dot of s, that is 1 upon 0.5625, and it will become 1.77. So this is my steam economy, and from the answer also we can write it up to 2 decimal places. The final answer, that is steam economy in kg per kg, as 1.77.